Hi there. Today we're going to look at Linformer Self-Attention with Linear Complexity by Sinan Wang, Belinda Li, Madian Kabsa, Han Feng, and Hao Ma of Facebook AI. So on a high level, this paper observes that often the way we build transformers, the self-attention matrix is low rank and can be approximated by first projecting the signal to a lower dimensional space and then performing these inner products that are responsible for attention in there. And thereby you save a lot of the complexity of multiplying full sequence length by full sequence length matrices, but instead do these operations in the lower dimensional space. And they achieve a linear scaling of the transformer attention, and we'll figure out how that is. As always, if you like content like this, consider subscribing, sharing, liking, and commenting if you feel like it. Okay, let's dive in. They say large transformer models have shown extraordinary success in achieving state-of-the-art results in many natural language processing applications. Okay, so these, if you don't know what a transformer model is, you can watch my video on the paper Attention is All You Need. That was sort of the beginning of these transformers, and it introduces the attention mechanism that we're going to look at today. If you don't know what an attention mechanism is, you're not going to have a fun time in this paper. They say, however, training and deploying these models can be prohibitively costly for long sequences, as the standard self-attention mechanism of the transformer uses n² time and space with respect to the sequence length. Now, why is that? So, pretty shortly, to recap this, the attention mechanism, these transformers, they transform, for basics, let's say they transform one sequence into another. So here we have 5 tokens, and the next layer will output 5 tokens. Okay, so 5 tokens in, 5 tokens out. And the question is, how do you route information between these 5 tokens from the first layer to produce the next layer? In a feed-forward network, you would simply connect everything to everything and sort of learn the weights of these connections. That's not what we do here. In a convolutional network, you would simply connect each node to its immediate neighbors like this. But this is also not what we do here. What we do here is we route the information according to the information itself. So according to the incoming information right here, we route the information that goes out. And we do that by expressing queries and keys. So this incoming information is transformed, first of all, into what are called keys. Now, keys are simply vectors. So each node is going to expose a vector right here. And each node in the higher layer, now these are produced by the same, from the same information down here, but I'm going to draw it conceptually on the higher layer. So each node here is going to expose a query, which is sort of like calling, the query is calling for what kind of information do you want from the lower layer, and the key is sort of exposing what type of information this node contains right now. Now the information is simply routed by looking at the inner products of the keys and the queries. So this information right here would probably be routed to this node right here, whereas this one would probably be routed here. This one would be routed here. In fact, this is a soft assignment, so it's not like a hard routing, it's a soft routing. Everything is routed to everything with different weights, but the majority goes to the place where the inner product is high, and this one is again routed here. So you can see this is the attention mechanism. In order to do this, we need to compute the inner product of every single one of these queries with every single one of these keys. Okay, and this, if our sequence length here is of length n, is going to require n² operations. Okay, now here is another parameter we need to pay attention. These vectors here, they have a certain dimension, and the certain dimension we're going to call d, the embedding dimension of the vectors. Now, in modern transformers, you can think of n as something like maybe 512 tokens go into a transformer like this. And the hidden dimension here also is in the same order of magnitude. So you can also imagine this to be something like 512. Now, if you think of these matrices, if you multiply the keys by the queries, however you want to, let's do it like this, then you have the keys are n by d and the queries are d by n, okay? Now, since n and d in this case are the same dimension, this matrix is of rank 512. Doesn't have to be, but it's a pretty good bet that it's of rank 512. Maybe it's approximately lower rank, but you know. Now, this isn't actually the modern way of transformers as such, because usually what we have is multi-head attention, which means that we're going to split this inner dimension right here. We're going to split these vectors into many, many lower dimensional vectors and then have attention mechanism on these lower dimensional vectors. And that's such that you don't only have one attention mechanism, you have multiple attention mechanisms, so you can route different kinds of information with these multiple attention heads. Now, sometimes you would split this. You could split this in a modern transformer up to like 16 different heads. But here we're going to, let's say we're going to split this into 4 subvectors, each of 128 dimensions. Okay, so we're going to split this up. And now if this product here is only computed on these lower dimensional vectors, so all of a sudden you no longer have n by d, but you have like n by d over 4. And now this is 512 still, but this now is 128. So the rank of this matrix is going to be 128. Mind, it's still, the thing that comes out is still a 512 by 512 matrix, but it is of rank 128. And that means even though this matrix contains vectors that are of size 512, they could be represented accurately by a matrix that's just 128 dimensions. Okay, so these 512 dimensions actually only contain information that is 128 dimensional in nature. It's just distributed over 512 dimensions, but most of these are redundant. So in fact, in these modern transformers, this matrix here is low rank, and therefore that's what this paper sort of exploits. We could approximate this by 128 dimensions. Okay, this is our starting point. They go on and they say, in this paper, we demonstrate that the self-attention mechanism can be approximated by a low-rank matrix. We further exploit this finding to propose a new self-attention mechanism, which reduces the overall self-attention complexity from n squared to n in both time and space. The resulting linear transformer, the Linformer, performs on par with standard transformer models while being much more memory and time efficient. All right, so let's dive into their thing. This is how they formulate the attention mechanism. So right here, the attention has queries and keys, as you can see here. Now, these W matrices you can largely ignore. The W simply maps the queries to, so these are simply D by D matrices that are a linear transformation of the queries. You can sort of overlook them for the arguments in this paper. So these are the keys and the queries we talked about. The values here, this is the actual information that's being routed. So what we want to do is we want to compute this product between queries and keys right here and scale it appropriately. But ultimately, this is this product. Then run this through a softmax operation. That means we normalize it such that it sums to 1, the distribution sums to 1. And then we want to route this information according to that distribution, okay? So that's how they formulate an attention mechanism. Now notice something. This thing in here, is what they call the matrix A, and this is what I've demonstrated to be low rank. Now, the actual thing that you would need to be low rank for their paper to hold is the matrix P, which is different because this is after the softmax, right? So if the matrix P is low rank, then you have a legitimate claim of approximating this routing via a low rank matrix. However, if P is not low rank, you don't, okay? All right. Now, the first thing they're going to show is that this is in fact low rank. So self-attention is low rank. And for that, they make an empirical investigation into Roberta. So Roberta is a model that's based on BERT, and I have made videos of both BERT and Roberta, I believe. If you want to go look those up. But it is one of these transformer models. And they take two data sets, Wiki 103 and IMDb, and they run them through this model, and they look at this P matrix. So they look at how this information routing matrix is built, and then they calculate the eigenvalues of that. So you calculate the eigenvalues, and by looking at the eigenvalues, you can look at the rank of a matrix, broadly speaking. So if you list the eigenvalues in order of their size, then a matrix that is sort of high dimensional, has a high rank, would have sort of a slope like this, and that means as you go to the next and next and next eigenvalue, they drop. Like if you order a set of uniformly distributed numbers, if you order them, then it would look like this, right? So there is no particular dimension that's better than any or has much more information than any other. However, if the matrix is approximately low rank, it would look something like this. And that would mean that most of the information is concentrated in very few dimensions. And those are the ones with very high eigenvalues. And most of the dimensions have no information. The thing you see here is simply the cumulative sum of these things. So if you calculate the cumulative sum of this, you'll get that over here. So if this is very high rank, you would expect a curve that goes like this, sort of slanted, but not very. If this is very low rank, you would expect a curve that goes very much into the corner right here. And they show that the general shape here is such that there is this kind of a kink to it, as you can see here. Now, also notice that the axis here starts at 0.4, so actually this comes from down here somewhere and goes up and then goes like this. So they have I feel they have a legitimate claim here that these matrices are approximately low rank. And here they look at, I don't actually know at which layer this is, or if this is in all of the layers overall or something like this, but they look at how this develops inside the layers. So they look at always the 128th eigenvalue, and they discover that as they go deeper and deeper into the network, this cumulative eigenvalue is higher and higher. That means that the network puts more and more information into fewer and fewer dimension in this routing as you go up the layers. So it gets more and more skewed. So as you go up the layers, it gets more and more into this corner right here. So their claim appears to be more and more true. Now, I have sort of thought about this a little, and I've tried it out a bit myself, and I invite you to just follow me here shortly. So right here, I have a matrix that is just a random Gaussian matrix of size 512 by 512. If we look at the eigenspectrum of that, so I have this function SVD that simply gives me the eigenspectrum of that, then you can see that it sort of falls off uniformly, and that will result in this cumulative sum of pretty much flat curve or slowly ascending curve like this. Okay. Now, if we actually have a low rank matrix, this would look different. This would have this sort of typical kink in it. And we can demonstrate that by making a lower dimensional matrix. So let's just go 512 by 128 of this lower dimensional M, and let's look at the MT. Now this only goes to 128 because we only get back 128 singular values. So let's make a lower dimensional matrix that's actually 512 by 512. So if we do this, this is sort of what they're doing in this. This will construct a 512 by 512 matrix, but that is only of rank 128, right? And you can see that at the 128th singular or eigenvalue, this snaps right at the 1. So it's sort of like what they have. Okay, so we've seen the difference between a, let's say, high rank matrix and the low rank matrix in this cumulative sum plot. Now I want to go back to the original matrix right here. Of course, the matrices they look at, these routing matrices, they're not Gaussian. They're not sort of distributed with mean 0 and the nice variance. They are the result of a softmax operation. And in particular, that means they're all positive. And that means that their mean is not 0. So if you look at a data set and its mean it's not 0, and you calculate like the eigenvalues, or in this case the principal component, you will find that the first one will be very strong, because that must account for the fact that the mean is not at the center. The first few will be like this. So it is sort of, maybe we can replicate this right here. So let's say we'll put M through, let's first go with the absolute value of M. Whoop. Okay, not much of a change, but you'll already see that this axis doesn't start at 0. So let's actually, how do we do this? Xlim, right? Xlim 0, none. Sahaha. Okay. So the first one you simply have to imagine, or I can do even something more. We can just put a 0 in front here, and that should do the trick. No? Yes. Oh, that's X. I meant Y. God, I'm a dumb. Never mind, this will work as well. So you already get this sort of kink, and let's put it into the softmax. So we put a softmax, and that gives you also this kink. Now you might think that, wait, this kink looks a lot smaller than the other kink. So, but if we simply let's modify the standard deviation of this random matrix, and you can see that this spectrum immediately changes, right? Because of the interaction now between the softmax and the standard deviation. If I only were to change the standard deviation on the normal M matrix, and we can actually try this right here, that wouldn't do much. That would still look pretty much the same. It's just differently scaled. But in the interaction with the softmax now, this changes the spectrum dramatically. And here, as you know, these transformers have always sort of like layer normalization and so on. So probably the standard deviation, if these are sort of Gaussian, the standard deviation before the softmax would be a lot smaller. So let's go something like this. So smaller than 1. And can we run this, please? And you can see that this kink immediately appears. Now it's not the same thing as this here, because this is a lot smoother, as you can see right here. But still, I feel that this might not actually be a result of the fact that this is an attention mechanism, but it simply might be the result of that you apply a softmax. Now, still, that doesn't change the fact that it is approximately a low-rank matrix. So everything they say holds, but yeah, maybe maybe one should also look into why exactly that happens. But in fact, it is low rank. Okay, it is approximately low rank. They've demonstrated this. And now they go to their first theory. Below, we provide a theoretical answer, a theoretical analysis of the above spectrum results. Okay, so the theoretical analysis, theorem 1, is self-attention is low rank. And we're going to go through this, just glance at it for now. They say for any of these query key values and these matrices, which of course you can ignore for now, for any column vector W of matrix VW, and W here, that's the information that needs to be routed, right? There exists a low rank matrix P tilde. So this P tilde here is going to be their low rank approximation of the P matrix. You can see it's still n by n, but it's going to be low rank. In fact, it's going to be of the order of the logarithm of the rank of the full matrix. Or, the full matrix of the rank that the full matrix could have. As we have already seen, the full matrix doesn't have full rank, but yeah. Okay. So if you use, and this is the type of guarantee you get. So what do we see here? It basically means that this distance here is smaller than this. And this here, this is just the norm of one of these vectors projected times this error coefficient epsilon. So all it says is that the distance on the left is smaller than something. And that occurs with high probability. Okay, so the entire guarantee here, the entire formula just basically means that this thing is small. This norm is small. What's this norm? This norm is the distance between these two things. Now, what are these two things? This is the information that we want to route, and this is the routing matrix. And that simply means that if I route my information using the P tilde, this approximation, then I won't be too far away as if I had routed my information using the original P matrix. Okay? That's it. That's what the theorem says. The theorem says if I route my information using this approximation, then I am not too far away as had I routed my information using the original routing matrix. Now, they don't say how they're going to construct. They simply say there exists a low rank matrix like this. And the proof of this, and it's sort of worth looking at the proof a bit, it uses the Johnson-Lindenstrauss lemma, this thing here, or the JL for short. And they're going to get this out of the JL. Now, the Johnson-Lindenstrauss lemma, in a classic sense, says something like this. If I have data in a high-dimensional space, here in a three-dimensional space, okay, I have data distributed, and I use a certain kind of projection matrix. And there are a number, so the JL gives conditions on what these projections can be, but for example, a randomly sampled matrix with 0 mean Gaussian entries and 1 over k standard deviation, where k is the dimension you project into, can do the trick. So if I project my data in a certain way into a lower dimension, here dimension 2, then the projected data is related to the original data by the fact that the distances between the points in the original space will not be distorted too much. So the distances between these points are approximately preserved through this projection. Okay, so that's the Johnson-Lindenstrauss lemma. Now, you'll notice here there is no reference to the fact that this data is or isn't low rank. It's simply high dimensional data projected to lower dimension, and the distances are approximately preserved. And this theory here, and I've looked at it for a while now, they simply define this P matrix as this attention mechanism, and here you can see the A matrix we've discussed before, which is actually low rank, but we don't know yet if the softmax is. They write it as this form right here of the exponential of each entry of A divided by this diagonal right here. So in the softmax, of course, you have the exponential of each entry divided by the sum of the entries, and they write this simply as two matrices, but ultimately this is a matrix right here, right? And all they do is they take this P matrix and they apply the Johnson-Lindenstrauss lemma by having this projection matrix R. And R is entries from this Gaussian, as I said. So this is the special type of projection that the JL addresses. And then it simply says, this here is going to be your P tilde. So if you project R in this manner and obtain P tilde, and then you use P tilde instead of P, then this is going to be very close. In fact, you can reformulate the JL into different variants such that it gives you things like this. Things like saying that the distance between this projected version and this unprojected version is going to be smaller than a constant times the norms of the unprojected version. That is equivalent to saying that the distances are preserved. Now, you can see right here, nowhere in this theorem is the fact that this is self-attention. And nowhere in the theorem appears the fact that this inner matrix A is low rank, or even that this matrix A exists. You can do this with any matrix P, right? The JL doesn't concern itself with the nature of this matrix P. It says any matrix, any sort of high-dimensional data you can project to low-dimensional data, and this holds if you choose the projection correctly, which they do right here. So to claim that this theorem proves that self-attention is low rank, to me is it's a bit of a statement that is not warranted. Like this here should read something like the Johnson-Lindenstrauss lemma exists, or something like this. I'm not sure. Like, convince me otherwise. But yeah. So they go with this. So they say, given the low rank property of the context mapping matrix P. Now, again, I disagree that this has been shown, except empirically. One straightforward idea is to use singular value decomposition to approximate P with the low rank matrix P low as follows. So what you could do is you could simply learn these low rank matrices and approximate P through it, or you can decompose P as such and then have these easier inner products in dimension K. But they say, however, this approach requires performing an SVD decomposition in each self-attention matrix, which adds additional complexity. Therefore, we propose another approach for a low-rank approximation that avoids this added complexity. Okay? So they now come up with their model. And their model goes as follows. So here on the left, you see a classic attention mechanism with their projections built in. What they're proposing is, they say, let's project the matrix K using one of these random projections. And then this attention routing, if you now multiply, so you multiply K and Q right here, K times Q, and then you put it into the softmax, and then you use it to route this W. So they say if we build in this projection matrix, that will project K to a lower dimension, and then we won't have as expensive of inner products. Now, the important part to see here is that if you think of this lower projection, the first thing you think is that you project this hidden dimension D, right, to a lower dimension. And that's not the case here. You actually project the N. So in a conceptual framework, so you can see right here, forget about this is this W matrix. In a conceptual framework, you see here is this N by D matrix, which are the keys. So N is the sequence length, and D is the dimensions. And what you want to do is you want to project that by this matrix, which is K by N. So you want to reduce the sequence length. And you can see in this matrix right here why that might work, because N is much larger than D. And that means this matrix can be at most rank D, right? So you should not lose too much. You should sort of be able to preserve the information. If you project this N to a K, where the K, if the K is still larger than the D, or approximately in the same order of magnitude, you should be able to preserve that information if you do it in a smart way. So conceptually, if we have our 5-token sequence like here, and the next layer produces 5 tokens again, what we first do is we say, we know that the information we want is not 5-dimensional. It's actually 2-dimensional. Because, okay, let's say this inner dimension D is 2 as well. So we have 2-dimensional vectors. Each thing exposes 2-dimensional vectors. So we first project this sequence of length 5 to a sequence of length 2. And we simply do that in a random manner. So we have a random Gaussian matrix that assigns weights to mix these 5 into these 2. And again, because the JL works for any sort of data, but in my argumentation, if you think that this here is low rank, it's of rank 2, then you shouldn't lose too much information by projecting it to a sequence length 2. And now we do this attention mechanism. So now we expose the keys, and now we expose the queries up here. And now you can see, instead of routing 5 things with 5 things, you only have to route 5 things with 2 things. And so instead of having O(n) squared, you now have O(n)k, if k is the number right here. Okay, so this is the idea. You project the sequence length, and it comes from the fact that the sequence length is much larger than the dimensionality, and therefore you can sort of preserve the information if you project in a smart way. They build this in this fashion right here. So the attention mechanism now, before we saw it was between the queries and the keys right here. They built now this projection matrix here that projects the keys into a lower dimensional sequence, and now such that this will result in an n by k attention matrix. We saw over here, you don't need to route n by n things, you need to route n by k. So this routing table in here is now n by k. Now the next layer, as you can see here, it actually needs to produce a sequence of length 5 again, right? So we always transform sequence of length 5 into sequence of length 5. But now we have this n corresponds to the next layer, and this k corresponds to the down projected sequence of the last layer. And in order for that to fit, we of course also need to down project the information that we're routing. So if we down project the routing table, we also need to down project the information that we're routing. We do this by a similar matrix F that is also sampled in this way, in this special way, and that gives us a k by d. So we have projected the sequence to size k, and if we multiply these two things again, of course, we'll get out an n by d matrix, which is the signal for the next layer. Okay, so an n by d signal comes in down here. It's projected down to k sequence length, and it's routed up again to n sequence length. And you have again an n by d matrix here. Cool. So that's how they do it. And they build this into the transformer. Now, as I understand it, these projection matrices, again, they're not learned. They are built up in this JL conscribed way. They are not learned. They are fixed once, and then that's that. At least that's how I understand it. So there are no more learnable parameters. Okay, so here they have a demonstration where they up the sequence length, and you can see the batch size decreases, but that's just to sort of keep the total amount of flops to be done the same. You up the sequence length and down the batch size. As the sequence length increases, the standard transformers requirement in inference time goes up. And this here, as you can see, this is not a linear scale, it's a log scale, log 2. So this goes up with the sequence length, and it should go up quadratically, right? And you can also see that the Linformer keeps fairly constant for the same k. Now, of course, as you increase the k of the Linformer, the inference time will go up, because now it's dependent on n times k and not on n times n. Okay. So let's look a bit further of how you have to choose that k. Up here in the first theorem, there was already a hint to it. In the first theorem, you had to choose k by 5 log n. And this is a problem. So here you have log n. That means it's not, so O of nk is equal to O of n log n. Now that's not linear. That's the same as the reformer, but they want to get to a linear place. And theorem 2 goes now to a linear, shows how you can make self-attention linear. Okay, they show, again, blah, 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 blah. Now you have to choose k at the minimum of these two things. And you can see right here that one of them is independent of n. So that means as n grows, of course, the minimum is no longer going to be this here. The minimum is actually going to be the thing on the left. And that is dependent on just d. Okay, so you have d log d in here. And that makes sense because in the very beginning, we said, hey, d is actually much smaller than n. And that means the information that is contained in these matrices is at most rank d. So if we down project to k, we should adjust k to what d is, right? If we adjust k to about the same thing as d, we're guaranteed to not lose too much information. So now we choose k according to d instead of according to n, and therefore the computation is linear in n. And n times k is like n times d to log d. So it's linear in k and linear in d. How do we get there? So the first thing they do is they make these sort of Johnson-Lindenstrauss statements again. But now instead of the general statement, they plug in their actual modified attention mechanism. So here they have a bound on the distance between if I route this is the information to be routed, right? If I route my information using the original softmax, and this in here is this matrix A, if the original attention mechanism, I won't be too far away as if I were to route my information using this modified attention mechanism. Now the tricky part here, mathematically, I believe, is that is exactly the softmax, what I alluded to, right? So this softmax is the tricky part, because if this weren't a softmax, so if the softmax weren't here, this would simply be a projection down and a projection up, and the lemma would almost apply as it is written, right? You wouldn't have to actually do anything. But the question is, if this inside the softmax is low rank, can you make a claim that the entire softmax then is also low rank? And it's not entirely clear because oh yes, we've done this. So you can see right here that the softmax, we haven't actually done the softmax of a low rank matrix. So we have already seen the low rank matrix itself and how it immediately snaps to the upper axis after 128. Now, if we do the same thing for the softmax of that, And we probably have to take away some of these dimensions, the first few. Let's go to dimension 100 and look from there. Okay, same thing. Okay, that's pretty good. I did not expect that. Hi there, so this is Yannick from the future. I've realized I've been an idiot in how I constructed these low rank matrices right here by multiplying MT by itself, of course. What's a better way to do it is to construct two independent 128 dimensional matrices, like these two subslices of M right here, and then multiplying those together and looking at the SVD. And as you can see right here, so the softmax of this is now not of this super low rank anymore. It's still low rank, but it's not it's not like hard low rank. So if I just look at the matrix without the softmax, then you can see it has a very peak that at the 128, which gives us the indication it's actually 128 rank, which we already knew. But if we now introduce the softmax, then you can see that this vanishes and it's no longer 128 dimensional, and it's only approximately low rank, as you can see. All right, back to Yannick in the past, who is wholly surprised that if you multiply MT by itself, that will give you back the exact same thing. All right, so did we try this before? Maybe we did. Okay, but the mathematical difficulty still remains, and their main thing here is, so they have a first version where they pretty much plug it into the JL again, and they get out this K needs to be by log n. But they say this result does not utilize the low rank property of matrix A, and the resultant K has a dependency on sequence length n. And then in the appendix, they finally go through the math to show that now if they choose E and F like this, they can actually pull out this and show that the K is, where do you have it? That the K is independent of n, like this. And I think the main step in this proof is the step B here, where they say uses the fact that the exponential function is Lipschitz continuous in a compact region. Then we can choose a small enough delta such that as you can see here, this now directly relates to this projection matrix within the exponential function to the projection matrix out of the exponential function. So you can basically say that if I project first and then use the exponential function, that's not too different than if I first use the exponential function and then project. Okay, so that's the sort of catch here. Now they only do this for the exponential function, not the actual softmax. As you can see here, throughout they do it to the exponential function, and also here in their statements. The softmax isn't the exponential function. The softmax is the exponential function divided by the sum of the exponential functions, but I believe that this generalizes straightforwardly. All right, so for given choices of delta and K, they have shown that the Linformer in fact can do in a linear fashion what a transformer can do in a quadratic fashion, and they are not too far off. Okay, that's their point right here. Their results on these benchmarks, let's first go to the perplexities in language modeling. So they show right here that they pretty much can keep up with the standard transformer, as you can see here. So with the standard transformer, they can keep up here. Now think that the computation is n times k. Okay, so something like this, a Linformer with k equals 256, will only, so instead of n by n, it's n times k. It won't save you too much in that case. But it's not too surprising that, in fact, you have the same performance, because probably the standard transformer is distributed over more heads than 2, so the information necessarily has a lower dimensionality than 256. One thing I want to draw attention to, though, here, is that you can see that here it's not really done learning yet. And as you can see, the standard transformer sort of surpasses all of these models towards the end. I wonder what happens. I wouldn't be surprised if they end up sort of at the same place, but I wonder if these diverge even more right here after that. They also compare with a higher sequence length, and the standard transformer outperforms the Linformer, but of course the point here is that the Linformer is much faster and can keep up. Now, also, the scale here of the perplexity, you see these are percentage points in perplexity, but I can't actually tell if that matters or not. I think in the original transformer paper, the perplexities hovered between like 3 point something and 5 point something. So this might actually be sort of significant differences, and I'm not sure. They investigate different methods of sharing these weights of these projections, and seems like they don't find real differences, but I don't want to go into that because this video is already really long. And then they look at what happens if they up the sequence length that they put into the Linformer. And you can see that the Linformer can deal with higher sequence lengths and arrive at the same perplexities. Though again, I don't know how much different that is, and the scale here is larger than before. But yeah. So how does this fare on these benchmarks, where you first train a transformer with pre-training with language modeling, and then you use it to do certain NLP tasks? And here you can see that the Linformer is on par in some of these tasks with the original transformer, but also you can see like a pattern where you can see pretty wild results in that, sometimes the Linformer here will be better than this, but then also variants of the Linformer will be worse, and they'll even be worse than this, and sometimes they'll be better. Sometimes this Linformer is good, and sometimes the original model is the best. So this sort of points to, you can make the general claim that the Linformer doesn't destroy your gains, but also it's not like a better model. It's simply a faster model that in some tasks can keep up with the original model. And they show that, of course, this is the real deal here, that as you go up in length, the performance gains, and also, in this way, the performance gains and the memory gains that you get by the Linformer are dramatic. Of course, the longer and you go and to the lower dimension you project, the more these gains are. But of course, the more performance you're going to lose potentially. Hello again, Yannick from the future. Just wanted to draw your attention on this beautiful broader impact statement in this paper, saying our work focuses on making transformers more efficient, everything cool, potential positive impacts of efficient transformers. That's pretty cool. It also has potential impact on training transformers on images, since we can support very long sequences. Very cool. Furthermore, there are positive environmental benefits. Very cool. These are all very cool things. They say, as such, we see no immediate negative ethical or societal impacts of our work beyond what applies to the core building blocks of deep learning. Do better. Now, honestly, I agree with them, right? I completely agree with them that this is sort of a good thing. You might trade off, some accuracy, you might make some approximations, but you'll get a much faster model. And this model, as any model, can be used, for things. And that they now have to pull out of their butt some way in over 5 steps of intermediate layers, this could be used for bad. It just seems ridiculous. So good on them for defying the please also think about negative impacts right here. All right, back to past Yannick. All right, this was the Linformer paper. I hope this somewhat made sense to you. I had to read it multiple times for it to make sense to me, but ultimately it's all about the fact that you have these multiple heads, and therefore your information is probably lower dimensional, and you can abuse that to just calculate in this lower dimension. All right, I'll see you next time. Bye-bye.